In this video, we're going to talk about computing volumes of solid regions. We're going to begin with the basic principle of volume, which you see here. This is similar to the basic principle of areas that we saw earlier. Suppose that you have a solid region S. So this is our region here. For example, imagine it's something that looks roughly like a vase, and you want to find the volume of that vase. So how does that work? Well, suppose that S is a solid that lies between x equals a and x equals b. So the base is sitting on the plane at x equals a, and the top is at the plane x equals b. Normally we think of the x-axis as being horizontal, but there's no reason that it can't be vertical like this. So here's the basic principle of volume. If the cross-sectional area at x is given by a at x, that is to say that this cross-sectional area here is a at x. So that's the area of the cross-section at x. So you pick an x value, like this one here, and then you slice into it, slice across, so you have this region here. This region is a cross-section, and suppose the area of that cross-section is a at x. Notice it depends on x. If I pick an x up here at the neck of the vase, the area is going to be smaller than in the middle, like this one. So it depends very much on which x you pick. So suppose that you have an x, and for every x you can compute the surface area, or the cross-sectional area. So if you can compute the cross-sectional area for each x, and you can write it down as ax, a function of x, then the volume of the solid is given by this relationship. The volume is equal to the integral from a to b of ax dx. Now, why would this be true? It's true basically for the same reason that it was true for areas of two-dimensional regions. Suppose that you pick your x and you draw a cross-section, but give it a little bit of thickness. So it's not a two-dimensional object. It's three-dimensional, it's just really, really flat. It's really, really narrow. So there is a thickness there, which we're going to call delta x. So then the volume is going to be approximately equal to the sum of all x's starting at a and going to b of the volume of this cylindrical region. Now, what is the volume of a cylindrical region? It's the area of the base times the height. The area of the base is a at x, times the height is delta x, which is a very small width or height. This will give you the approximate volume, and then you compute the limit as delta x goes to 0, and the result is going to be this definite integral from a to b of a of x dx. This sum here is a Riemann sum, and as delta x goes to 0, your Riemann sum goes to an integral. And that integral will be the exact volume. Exact volume. That's why it's true. Now in this picture, we've drawn the vase sitting upright, just so that way we could visually imagine a vase sitting there. But we could easily imagine that the vase was lying on its side. Something like this. And we can imagine that the vase extends along the x-axis from x equals a here to x equals b here. And again, we imagine that we can pick an x between a and b, and we slice through to get a cross-section. So sometimes this is known as the slicing technique, or the cross-sectional technique. And then what you see here has area ax. It's the same thing, just on its side. It doesn't have to be horizontal, it could be vertical. Or instead of being vertical, it could be horizontal. Let's actually look at an example so we can see exactly how to use this. Example. find the volume of a cone of height h and having base a circle with radius r. So we have a circle as our base, and the circle has radius r. And the height of this cone is h. So it looks something like this. So the height here is h. Now you may know a formula for the volume of a cone having height h and base with radius r. But where does this formula come from? Well, we can imagine drawing an x-axis like that. And let's imagine that the point of the vertex of our cone is at, say, the origin. So let's draw a y-axis here. And we're going to lay the cone down like this. And let's draw the other side in like so. And now this is a cone. So let's pretend that this is a circle. Let's pretend that this is a circle at the base of the cone. Now, we haven't drawn the cone vertically, we're drawing it horizontally just to make it a little bit easier to visualize. At least visualize what we're going to do next. So the idea here is that we've laid this cone so that its vertex is at x equals 0. So this is x equals 0 here. And the height of the cone is h. So right here, that's going to be x equals h. So what we have is a solid object laid from end to end. It's between x equals 0 and x equals h. The next step is to find the cross-sectional areas. So pick an arbitrary x like so. And then we slice through to get a cross-section. Now this is going to be a circle because this is a circular cone. So that's a circle. Let's shade it in so it's blue. And let's call it a at x. A of x is equal to the area of a circle. How do we determine this area of the circle? Well, the area of a circle, of course, is going to be pi times r squared, where r is the radius of the circle. The radius of the circle is this length right here. That's r. Well, notice that that's actually y in this picture, because it's measuring how high above the x-axis it is. But how do we actually determine what this value is? Well, notice that if you think about just what we're looking at here, it looks like we've drawn a triangle. That's because this is flat. It's actually a cone, but let's just focus on the flat portion here. Let's just draw in this right here. So now you can see that we have two right triangles. One right triangle is this large right triangle right here. Let me just highlight that in green. So we have this green right triangle. So this isn't the cone that we're looking at. We're just looking at the small slice of the cone, which is a right triangle. Similarly, we have a smaller right triangle here. Maybe I shouldn't use blue since we're using blue for the circle. So let's say gray. Let's just fill it in. like so. So now you have the smaller gray triangle, but this is also a right triangle. So again, we're just looking at these triangles. You can imagine rotating these triangles, or rotating the big green triangle around the x-axis, and that would generate the cone. That's what we call a solid of revolution. So what we want to do is we want to determine the area of this circle. Now, in order to do that, we want to find the radius, because the area of the circle is pi r squared. The way we're going to do that is by observing the fact that the green triangle and the gray triangle are similar. They're both right triangles, and they both share this angle at the vertex. So that means they're similar triangles. So now we can find r by looking at it as a corresponding side of these two similar triangles. So this length here, that's r, capital R, because the base of this cone is a circle having radius capital R. So capital R to little r, that's the altitude of this the big right triangle to the little right triangle, is equal to the base, which is h, of the big triangle, to the base of the little triangle, which is x. This length right here, that length is x. That's what x measures, how far away from the y-axis you've gone. So if we want to figure out what little r is, we cross multiply. Capital R times x equals h times little r. Solve for little r. Capital R over h times x is equal to the radius. So that's the radius of our circle, of our little circle. So that goes in here. So then the area as a function of x is pi times this radius squared, where this radius is r over h times x. So now all we have to do is integrate. So the volume is equal to the integral from 0 to h of ax dx, which is the integral from 0 to h. And this radius, this area rather, we've already found it. It's pi times r, little r, which is capital R over capital H, times x squared dx. We can simplify this, of course. This is r squared over h squared times x squared. R squared and h squared are constants. Pi is a constant, so you can take all of those out. So you're going to have pi times r squared over h squared times the integral from 0 to h of x squared dx. On this we can use the power rule. So this will give us x cubed over 3 from 0 to h. Let me make that a little straighter. 0 to h. Now, of course, when x is equal to 0, that's just 0. So we're going to have pi capital R squared over capital H squared times capital H cubed over 3. And if you simplify that, you get 1/3 pi r squared h. And if you remember the formula for the area of or the volume of a cone, that's exactly what it is. The cone is a familiar object, something that we understand what it looks like. But the beauty of this technique is that it will allow you to compute volumes of regions that are even difficult to visualize, so long as you know the cross-sectional areas. So let's look at another example. For this example, suppose S is a solid object with base in the xy plane So the base is sitting in the xy plane, but let's say it's a circle. So suppose S is a solid object with base in the xy plane having the base the unit circle. So let's say the circle with equation x squared plus y squared equals 1. So S is a solid object with base in the xy plane having base that circle, the unit circle. And suppose cross sections perpendicular to the x-axis are squares. What is the volume of S? So we want to find the volume of this object, which perhaps is not easy to visualize. What we do know is we know what the base looks like. The base is a circle. So let's draw a circle. There we are. Now we're going to claim that this is the unit circle. That means its center is at the origin, the point 0, 0, and the radius is equal to 1. So this point right here has x-coordinate 1 and y-coordinate 0. This one here has x-coordinate 0, y-coordinate 1, and so on and so forth. The radiuses are. The claim here is that this is the base of our object. And the cross-section's perpendicular to the x-axis. Well, this is the x-axis. So cross-sections perpendicular to the x-axis look like this. And this says that they're squares. So what that means is that there's a square sitting right here on this line. Imagine you're looking straight down at it from above. You wouldn't be able to see the square. It would just look like a circle that you could see. But there's a square sitting right here. Square sitting on the circle. So you could imagine if it was sitting, if you imagine drawing the circle on the ground, then there's a square sitting on top of it like this. So this is the square. Importantly, what that means is that it has the same height as it has base. So what we need to do is we need to figure out what the base is. Because the area of this square, let's say the area of the square is a at x. So that's the area of this object right there. Area equals a at x. That's the area of that square. Now it's a square, so it's length times width. But length and width are the same because it's a square. So if you can figure out what the width is or the length is, then you just square it and that will give you the area. Okay, so how are we going to do that? Well, we know what the equation for this circle is. The circle is x squared plus y squared equals 1. So in particular, for a given x, if we say that that's our given x, we can figure out what the length is of this line because we know what the coordinates of these 2 points are. Let me just copy this and paste it. So I just want to copy and paste it so that way I can work with it a little bit. Let me get rid of all of the extra stuff here. All right. I'm going to get rid of these 2 points there. All right. So we know that this equation, so the circle has equation x squared plus y squared equals 1. If we solve for y, then we get y squared equals 1 minus x squared, and y equals plus or minus the square root of 1 minus x squared. Now the plus and minus correspond to the separate halves of the circle. The top half of the circle is y equals the positive square root of 1 minus x squared. And the bottom half of the circle is the negative sign, minus the square root of 1 minus x squared. So what that tells us, if this point is x, if x is right here, right there, then this coordinate of this point right here, the x-coordinate is x, and the y-coordinate is the square root of 1 minus x squared. Similarly, down here, the x-coordinate is x, and the y-coordinate is minus the square root of 1 minus x squared. Now the base of this square is the distance from one point to the other. It's the distance from this point to this point, this length. Now they both have the same x value. This is a vertical line. So if you want to find the distance from one point to another, it's just the difference between the two y values. So what that tells me, if I call this L for the length of the square, L is equal to the square root of 1 minus x squared minus a square root of 1 minus x squared. Of course, minus and minus is a plus. So you end up with, since these two are the same, 2 times the square root of 1 minus x squared. That's this length right here. That's the base of, if you look over at your square here, the base is L. So we could put a little L here. But of course, the height is also L then. The area of the square is going to be 2 times the square root of 1 minus x squared, quantity squared, which is 4 times 1 minus x squared. So that's the area. So if we want to compute the volume, that's going to be v is equal to the integral. Well, what's the smallest x value? The smallest x value is over here, which is minus 1. The largest x value is over here, which is plus 1. So this entire region is between x equals minus 1 and x equals plus 1. So we're going to integrate from minus 1 to 1 ax dx. But we know what ax is now. It's minus 1 to 1, 4 times 1 minus x squared dx. You can take the 4 out if you want. Then you're integrating from minus 1 to 1 of 1 minus x squared dx. And we can do each of these individually. That is, we know the antiderivative of 1, and we know the antiderivative of x squared. So the integral of the difference is the difference of the integrals. So namely, the antiderivative of 1, or an antiderivative of 1, is x, minus an antiderivative of x squared is x cubed over 3. And then we want to evaluate this between minus 1 and 1. Okay, so this is going to be 4 times, if I plug in the 1, I'm going to have 1 minus 1 cubed over 3, minus, and now we plug in the minus 1. Now it's just a matter of working out what all this is. This is 1 minus 1/3, which is 2/3. Over here, we have minus 1 plus 1/3, which is minus 2/3. So we have 4 times 2/3 minus a minus 2/3. Again, minus a minus is plus, so that's 4/3. So you end up with 4 times 4/3 is 16/3. Even though perhaps with this problem we were not able to visualize what the three-dimensional object looked like, we didn't need to. We knew what the base looked like, and we knew what the cross-sections looked like. And in order to compute the volume, it was sufficient to integrate the cross-sectional areas, and that's something that we could do even if we didn't know what the region looked like.